Thank you. You did well. Thank you very much. Very happy to see all of you here. My name is Oleg. I work for Oracle. I work with the GraalVM team at Oracle Labs, which is a research and development team within Oracle, and the main contributor power behind the GraalVM. If you have any questions that you don't want to ask me personally, you can find me on the internets. I'm almost universally go by @Šelajev, so you can tweet at me and we'll try to figure out things and answers to your questions. Before we start, because the session is called New Opportunities for Java Developers, how many of you think that they are mostly Java developers day to day? How many of you use other JVM languages? Scala people? Kotlin? Right. Groovy? Excellent. We did some exercise in the morning. Enough. Right. So I will try to concentrate mostly on Java rather than the other languages, but we'll try to cover all of them. And we have 50 minutes, so we'll dive right in and go hard and fast, just like we like our software to be. Before we actually go into technical details, please do not make any forward-going business decisions based on the contents of this presentation, which is very important. And let's talk about GraalVM. How many of you have heard of GraalVM? Excellent. That's very nice. That makes my heart as a developer advocate for GraalVM very warm and pleasant. How many of you think you can explain what the GraalVM is? Right. So you're in the right place to learn about this. I'm in the right place to help you understand what it is. In one sentence, it's a high-performance polyglot virtual machine that supports many different languages, and it's embeddable in native and Java applications. Right? It's a long sentence. There is a lot to decipher. It's high performance. It means we would like to run your programs fast. It's polyglot, meaning that we can support and run programs in different languages. And you can mix those different languages inside a single program if you wish to do so. It's embeddable. It means that you can enhance your existing application, whether that is a Java application or a native application, with the capabilities of running code in different languages. And that's it. So you get high performance, polyglot, embeddable virtual machine. Right? Why would you be interested in that? There are a number of use cases for what GraalVM can do, and it's a very versatile project. It can do many things. Some of them are more obviously useful to developers than others. So if you think, why would you be interested in GraalVM? So first of all, it's a really very good runtime for running your applications. If you are writing your applications, if you're deploying them somewhere, if you are waiting for them to finish or process user requests or some data, and you would like that to be fast, GraalVM is a great choice of a runtime to look at, right? Because it could be indeed faster than other choices. There is a special thing about GraalVM that can make your programs, it can compile your programs ahead of time to the native executable, and in that mode, your programs will have different performance characteristics, right? It will start up really, really fast, like in milliseconds, comparing to the startup of the native programs written in other native languages. And it will have a much lower memory footprint that you would normally expect from a Java program. You can embed GraalVM if you have a platform, if you have a large piece of software that you would like to enhance with the scripting capabilities, and you would like to support different languages, you can use that with the GraalVM stack, and it's fairly straightforward to do so, right? If you write a large streaming platform, right, or if you are writing a graph database and you would like your users, developers, to be able to configure that or query that using different languages, you can use GraalVM. Or if you have a library, for example, it's a very interesting use case. You have a library and you want to expose that library to different ecosystems, right? You would like people who are writing Node.js to experience the power of the null pointer exceptions that you write in your Java code. You can do that and they can consume your library from their Node.js code. And of course, you can write polyglot software, which is maybe not the most straightforwardly useful use case, but you can build systems where different components are written in different languages, and they operate and they work at runtime without any overhead for converting data between different languages, right? So if you have a use case for that, if you have people on your team who would like to use different languages, for example, you could maybe use Python or R for data science or machine learning, or if you would like to reuse other components from other ecosystems, you can do that on GraalVM naturally. In one picture, it looks a little bit like this. All that goodness, all the capabilities of the GraalVM, so the ability to run different languages, they are the inherent capacity of the GraalVM, and you can run programs in all those languages. So the currently supported are the JVM languages, naturally, right, coming from the JVM itself, right? We have support for JavaScript, we have support for Python, Ruby, R, and we have support for native languages and everything that goes through the LLVM toolchain. LLVM toolchain is the compiler toolchain. They have an intermediate representation for the programs, kind of like Java bytecode, and we can take that and we can run them on GraalVM, so you can run your native applications there as well. And you can run all programs in those languages in different contexts. You can run them inside the JVM, like a normal Java process. It will be probably built of OpenJDK, and you will start that using the Java command, and it will be normal Java, and it will support whatever your program in Java does, and that would be compatible. You can run it as a Node application, and that would be proper for reals. It will be Node. It will have the event loop. It will have the signal handlers that Node registers. It will provide the platform for the application as normal Node does, right? So everything that is expected to work there would be expected. GraalVM is built in certain experimental builds of the Oracle database, which you can try, and you can use that to, for example, write your stored procedures inside the database using JavaScript. Normally you would do that using PL/SQL, but if you don't want to use PL/SQL, there is an option to maybe use JavaScript or Python in the future. And you can compile your applications ahead of time, and then they will not depend on the JVM, and it will be just a native binary that you can throw into this empty from scratch Docker container, or you can just throw it on your server, double click on it, and it will run in a different mode than on the JVM, right? But the languages are supported by the GraalVM and sit within it, and it's just the platform that is used for running it is different. So that's how it works. How it looks from the inside, because people tell me that a picture is worth a thousand words. It looks like this. So this is what you get when you download GraalVM, and you can download that from the internet, and you can unzip the archive, and you will get something that resembles the normal JDK, which is probably the most important bit to Java developers, right? You recognize the normal Java commands. You have your Java C compiler. You have your Java command to run this. You have your utilities like JMap, Java P, and so on. There is a jar in the corner somewhere, but you also have other things that you will not find in normal JDK distribution, and they're unique to GraalVM. So that's support for running Node, that's support for running Ruby, or Graal Python, or R, and the support for the GU utility, which is the GraalVM updater, which is the thing that allows you to install additional packages. How it works on the architecture level. When you run your programs, it's a little bit like this. You start the platform, and in the normal use case, that would be the JVM, and that would be the Java hotspot VM. That would be normal Java. And actually, in our builds, it comes from the OpenJDK project. And then we enhance that with the GraalVM compiler that integrates with hotspot using the JVM CI interface, which stands for JVM compiler interface, which is the thing that you have to implement if you want to supply a third-party just-in-time compiler for your Java. Through that, we can run all normal Java bytecode, and all Java applications would work. And you can just use that normally as the runtime for your Java applications. And then for support for other languages, goes through a special framework called Truffle, which offers you an API to implement language interpreters. And then those language interpreters will be compiled at runtime and be optimized at runtime, and will produce a very efficient code for programs in those languages. Right? The same thing can work without the dependency on the JVM, but then you will currently lose the ability to execute Java bytecode because, well, there is no JVM. And you will enjoy the same stack for running other languages, but since there is no JVM, those Java bits are cut off. Right? If we run this in the context of a node application, or if you want to understand how to embed this, then it looks approximately like this. You start your node application in its normal node, and it links in the hotspot, which initializes the Java virtual machine compiler interface, connects with the compiler, and then you can run things the same way, but this would be just within the node process. Or, for example, if you have like a large application that you want to enhance with this, that Node.js logo will be your application. So when we embed this in the database, then that would be the database logo, right? And the same thing you can run without the JVM as well, where you would have the pre-compiled ahead of time version of the necessary components to run your languages and programs in your languages. How do you get this? It's an open source project. It's available on GitHub. You can go there. You can see what the code looks like. You can download it. You can load up in the IDE. All of the code is written in Java. So this is one of the interesting bits about the GraalVM project. The compiler is written in Java. The runtime bits necessary for running as an ahead-of-time compiled program are written in Java. The language support is written in Java for all the languages. So it's all Java. So as Java developers, you could be pretty happy about this because you can reuse the tooling that you know and love, right? You can fire this up in your IDE. You can go through the links. You can go to the definition. You can pretend that you understand how the compiler works. I certainly love to stare at the code and do pretend that I really am a compiler engineer. I will get the commits eventually, but like proper compiler optimization commits one day. But it's certainly much easier to do that than, say, with the runtimes written in native languages. How many of you speak like fluent C, C++? Very good. Not very many people. Good for you. You will be very valued professionals, and I hope you are currently as well. But so for the others, this is much more interesting virtual machine implementation because it gives the ability to understand things better. If you don't want to build your stuff, the GraalVM distribution from GitHub, you can just download the binaries. You can download the binaries from the website. It's called graalvm.org/downloads. There is a community edition, which is the open source bits out put into the archive and built for you. And there is an enterprise edition, which you can get currently for evaluation from the Oracle Technology Network, which eventually you would be you will need to purchase. And the main difference between those is that the compiler, the just-in-time compiler in the Enterprise Edition is more sophisticated. It has more optimizations. It does a better job at optimizing your code at runtime, so it produces a faster result. They're functionally equivalent, so the programs that are running on the Community Edition can run on the Enterprise Edition and the other way around, so you can opt into choosing the Enterprise Edition if you wish so. But you can enjoy all the benefits with the Community Edition too. And just recently, last month, we announced that the Oracle GraalVM Enterprise Edition becomes a proper product, so which gives the longevity to the project. And supposedly, Oracle could support this until the heat death of the universe, as long as there are people who want to support. And the GraalVM Enterprise comes with a better just-in-time compiler, so it means more performance. This is a very important topic. When we say more performance, when we say it's a high-performance runtime, what do we mean? What does it mean to have better performance than something else? And it could be, like, for everyone, it could be, oh, this is like a natural question. It just runs faster, or it starts up faster. Certainly, there are many sessions where, even here at the conference, where people emphasize that better startup is better performance. But in reality, performance is a complicated matter, right? There are many dimensions to that. It could be the startup, and that could be important in some use cases. It could be better peak performance, the throughput, how many requests you can serve per second, how many users you can handle with a certain set of hardware. Could be the memory footprint, right? How many users you can handle if your hardware has X gigabytes of RAM. Like, can you scale horizontally? Maybe it's the maximum latency. In some use cases, you really don't want any pauses. You want every request to come back as soon as possible, right? It could be a smaller amount of requests per hardware, but the maximum latency could be very minimal. Or it could be packaging size. So performance means different things to different people. How many of you think that when they hear performance is the peak performance? Like how many things we can run at once? How many of, not many. Startup? How many people don't understand what we're talking about when we talk about performance? Right. Excellent. So we're going to concentrate on peak performance first, and then we're going to go into the startup time and memory footprint a little bit later in the session, because those are the things where the GraalVM distribution, sorry, there is an animal flying here, where the GraalVM distribution shines, right? And we start with a demo, and I will show you a benchmark, and you should be a little bit skeptical about this, because whenever somebody shows you benchmarks on stage, you should be considering replicating that in a more scientific, rigorously proven benchmark environment. So I'm in my terminal here, and I'm in the GraalVM. I downloaded GraalVM, so I'm sitting in the GraalVM bin folder. You can see it's a GraalVM Enterprise Edition 1902, which we released recently. And when I look at what is here, you can see that there are all those commands that I showed before. GraalVM is configured as a default Java on my machine. So if I do which Java, it's supposed to point me here, right? So whenever I run Java on this machine, right, and for you here, you know that it's our Java that is running. There are no trickery unless specified otherwise. And even you see when we run Java version, it's Java 8 build, recent build of Java 8, and it's the GraalVM Enterprise Edition. So this is fairly important because our builds, the binaries that we provide as a team, are Java 8 based. How many of you run software that is like running Java 8? Excellent, good people. How many of you run on something older, 6 and 7? Any Java 5 people? I don't see, is that a hand or not? But no worries, mostly Java 8. How many of you run Java 9 plus? Yay, progress. Java 12, I think that's the contemporary one. Excellent, nice. Right, so most of the people run Java 8, which is very good because we did the binaries for Java 8, which means that you can download the zip archive, you can unzip it, you can change the path to this Java, and you can figure out whether that brings you performance benefits or not. Let's see, let's look how it works. Imagine I have a simple benchmark, right? And that would be a very small file, right? For example, where did we go? No, quit. So we have a benchmark like this. It's a JMH benchmark. We have some values, and we have one test method that exercises the stream API from the Reactor project, right? Project Reactor is the core library that implements the reactive streams and is used in Spring applications when you do reactive Spring applications. So we use Flux, and we're just going to parse this data, and we're going to map some functions, and we're going to sum them up, and we're going to wait for the return result, right? Small method, not necessarily the method that has the most business value for your employers and your projects, but it could be similar, and what's more important, it exercises the past in the code that most probably your web applications exercise as well, right? Meaning the reactive stuff from the project reactor. What I can do, I can just run it now, and I will run it for the suspense purposes, disabling our compiler here. So I will say, don't use the GraalVM compiler, use the normal stuff. That would be then the top tier compiler, and we'll run this because it will run for a few seconds. The top tier compiler in this setup will be C2, right? So your code starts loading, the JVM starts executing that, then it figures out, oh, this particular piece of code is hot, it's executed many times, let me optimize that. The compiler, please take it, give me the machine code for this, and then it does something with the machine code, right? So it runs, you can see the results get a little bit better, and it's just, the benchmark is very simple. We measure the time that it takes to do one iteration of this method, right? So we process all the integers in that array, and we just stream them through the Flux reactive thing. The output, the actual numbers are not relevant because it's not the rigorous scientific benchmarking environment. But you can see that when I disable the GraalVM compiler, it takes something like 2300 nanoseconds per operation, right? If I now run this without disabling the GraalVM compiler, right? So this would be the same JVM, but with the compiler included, which is by default in the GraalVM environments, in the GraalVM binaries, we'll see the different results, right? How different is an open question, always. So in this particular example, they would be significantly different. In many other examples, they will be also significantly different. But what I would like to recommend you is to evaluate always on your code. You can see that even now in the first warm-up iteration, the results are ridiculously better than previously, so 89 nanoseconds per operation. So the GraalVM compiler actually sees through whole that pipeline and does the smallest amount of work for that code. So we know the results now. We have 80 nanoseconds per operation here. Let's add the error back. So let's say 100. And before, we had 2,000. So that's 20x difference, which never happens in real life for any performance work. 20x is ridiculous. But you can expect that, I hope you realize that there are no trickery involved. There are no specific optimizations in the GraalVM compiler that says, if you see an array of 100 elements, and that array is passed through Spring Reactor project, then please optimize this very carefully. There are high-level optimizations in the compiler, right? We have state-of-the-art inlining, we have great polymorphic inlining, which means that the compiler sees through larger pieces of code. We have great escape analysis, which means that we can reduce the allocations, and we can make the impact on how much GC is running, and we really shine at the high-level optimizations. Now, I can show different benchmarks. For example, I can run a certain, this one is a cool one. This one is a cool one, object hash. This is a short code, right? I will just have a object with a couple of fields, and I will run objects hash in very abstracted code, right? High level. This is how we like to write our programs, and I will pass those things in the object hash, and I will compare that to the raw implementation of this, what object hash does. So it's just manually computing the hash code for this. If you are not aware, then objects hash takes the var args and it calls the hash code, and then inside the hash code, it does the same thing, but for every element of the past array, right? So it does some sort of, it has an abstraction that makes it easier to use in the code, but it also has way more code. So when I run this when I run this thing with, which Java I have here, Java minus version. When I run this, and this is normal Java, I will run this Java minus jar target benchmarks, and I will say I would want to write raw benchmark, right? Just 10 seconds, we could wait. So it has good results. It just math, right? We just multiply 3 numbers, all good. You can see that it has 1 value. So we have operations per unit of time, so higher is better. And then, but if we run the abstracted version, right? When we When we run the abstracted version, you can see that performance suffers because the compiler cannot optimize that code as well because there were more abstractions. So it's harder for compiler to see through that. So you can see that there is a significant difference. Right before it was what? 400 operations per nanosecond, a microsecond, sorry, and here is 60. So when I run the same benchmark with the Java from the GraalVM thing, right? This is RSL. Now I will just run this last one just to show you that the performance of the abstracted version does not suffer, right? It's a more abstracted code, but you can see that it doesn't matter. For the good compiler, there is no matter how much abstractions, no, there is a limit how much abstractions you can throw at it, but it's much higher than for other choices that you have. So this means you can build the code and write the code the way you want to write it. You don't have to like trick it and make sure that your code fits into the inlining limits or manually inline things. Of course, you can configure and you can write code that is easier to understand by the compiler, but you don't have to, and you don't suffer any performance penalty for that, which should be very good because as developers, we would like to write the code that is easy to read because it's written for people to read and occasionally for machines to execute, right? So it's a good high performance runtime, which is not maybe the most interesting bit, but it's a very important bit because very many people think that GraalVM, for example, is just this ability to compile programs ahead of time to the native executable. It's a solution for the startup thing, and do not realize that it's actually a compatible JDK that you can just use and run and see performance benefits, right? It shows good results on different benchmarks, both small and large. It shows different and very good results for different JVM languages. Scala people definitely should look into this because you get double-digit performance increase with whichever versions of the GraalVM that you are trying to use. The easiest way to try GraalVM or the technology in that is to use a version of the GraalVM compiler that is provided with the OpenJDK distribution. Right? There is actually, if you use JDK 10+, you can just enable this with 2 command line options. You unlock experimental VM options. You say, I would like to use JVM CI compiler, and you will be running a version of the GraalVM compiler. So if you have an environment where you can do some performance measurements, I would recommend you to just turn it on, run it, and measure some results. It could be the timing of batch jobs, or it could be the timing how long it runs the tests, or certain things like that. It doesn't have to be very scientific, but it's very easy to try. And if we show really good results, and it works very well on very modern Java workloads. So this is the high-performance build. Why do we want more benchmarks? Because if you run just few benchmarks, you will overfit on those specific benchmarks, right? If you only measure your performance on I don't know, a certain piece of code, you will be really good at that, but most probably you will not be as excellent on the general purpose code. So you can look at the modern benchmarking suite called Renaissance that we recently started and published. Don't go wild with the conclusions that we should only run everything on GraalVM. Personally, I would be very happy if you think that, but be more conservative with your conclusions. And you can always run your applications that you normally run with Java on GraalVM as well. So if you run an IDE, you probably run it for months without restarting, or at least days, you can turn on the GraalVM compiler or use the GraalVM distribution to run that and speed it up. Because snappier IDE is always a good thing. Right. Let's go then into the other dimension of the performance, which is the startup and memory overhead. As I said, GraalVM can run and optimize your code as a just-in-time compiler, and that would be in the context of the JVM, or it can compile things ahead of time with the native image utility that is in the current builds is available as the early adopter technology. So there's a utility called native image. You can feed your Java classes to that, and it will produce the binary that you can execute afterwards. How it works? It's very important what it gives you. It gives you two things. It gives you the startup in milliseconds. It gives you the memory overhead in megabytes. It takes your application, it takes your libraries, it takes the classes from the JDK, it takes the runtime bits from the implementation of the runtime components necessary to run, so like a garbage collector implementation from the project called Substrate VM, and runs some heavy analysis. It determines what calls what, it determines how to optimize this, builds the full universe of all the bytecodes that ever will be executed, and then it compiles it ahead of time, and it writes it into the binary. It pre-initializes some data structures, and it writes that in the binary. As a result, the startup is absolutely excellent. So, the startup. On the JVM, when you run as a JIT, you will need to do a bunch of things, right? You will need to initialize the JVM, load the classes, verify things, interpret the things, run the initialization, then you need to pass the classes and the bytecode through the compiler chains, and then you run with the machine code. In the ahead of time compiled world, you just load things and you run as you would expect, with a very predictable, good performance from the very start. The memory footprint is kind of a similar story. On the JVM, because it's a complex application, you need to do many things. You need to load all those classes, you need to verify the code, you need to compile that. That takes memory, because it initializes data structures and whatnot. In the ahead-of-time compiled world, there is no machinery to do that. You just load the code that is actually needed for your application to run, you load the application data, and you run with it. So that's how you can reduce the memory overhead of your application significantly. And then some people say, oh, but there are things that do not work in the GraalVM native image thing. For example, how can I do reflection? And there are impossible to do reflection because, well, you need the closed world analysis. You need to statically analyze your application, and then it will break reflection because they are operating dynamically at runtime. Or how well I will do proxies because proxies are generated at runtime as well. And it's impossible to cover them with a static analysis. And this is true. It is impossible to cover them with static analysis. What is possible, though, is to, as a developer, to provide configuration to the static analysis, saying that, oh, you know what, I will be doing reflection here. And that configuration can be taken into account, and the necessary classes and components could be included in the final image, because the final image, actually, that's a very important bit. The final image doesn't include anything that is not used by the application. That's why it's small, right? It's also very nice from the security point of view because, well, if you don't include code that you are not using, you don't include vulnerabilities from the code that you are not using, which is very good because you reduce your surface for vulnerabilities. But that's the other point. If you don't configure to include necessary things that you use dynamically, they will not end up in the final image, right? So you need to configure that. How do you do that? You can do that manually. There is a configuration file that you can do. But you can also use the assistant configuration and a Java agent that will generate this configuration for you. So imagine you have a code like this that does some reflective access to some methods. And we will just say, sorry, that we would like to get a method, and then we would like to invoke that, and we don't know which methods we would like to invoke because that is just the command line arguments, right? So until we actually are at runtime, we don't know which methods to include in the image. So obviously, if you just build the native image, or if you will try to build the native image of this application without any configuration, then it will not include the methods that you would actually want to run. But we can, so we can Java C this hello reflection class, and we get what do we get? We would get the class file, and we can run it, and we can say foo and say buzz, right? So the foo method is in there, so we can run it, and we run it through a reflection access, and then when say we want to run buzz method, then we don't find it, and we throw an exception, right? So it's a normal Java behavior. How can you build a native image out of this? You use the assisted configuration. So I will show you the command line here. What you say, you want to use the Java agent. You have the pass, and you have some configuration where to write the output files. And you just run your Java application normally using your normal Java, and it will just generate configuration for you. So when I run this, come on. Run Java tracing. It will run the same way, right? But it will also create me a meta-inf directory here. And in that meta-inf directory, I can do meta-inf, native image, reflection configuration, and you can see that there will be the JSON file. Oh my God, what I'm doing. Go back. There will be a JSON file that says that we will need to include this particular method that we recorded being used at runtime when we run our Java application. So now after that, with this file in place, I can just do native image, which is a utility inside my GraalVM distribution. I can do native image, and I can just say what's my hello reflection, right? Usually you would pass the what? No. Right. Yeah, it works. Usually I would feed my whole class pass into the native image utility. I would provide some additional configuration. I will provide the command line options. There are tons of knobs and configuration items that you can do. But in general, it will just take all the jar files, find the classes, and it will run, and it will output me a file. And I can run this, and you can see that it will produce me the same result. Because what? Because you had the configuration to include reflection, and as you could see, I didn't write any configuration files manually. So obviously, the configuration will be generated only for the code pass that you actually touch when you run your Java command, right? When you run your application on the JVM. And that's kind of expected, because if you don't execute that code, the configuration for that code could never happen. So you might need to manually configure it additionally, or you might need to touch those code paths on the JVM. A very good scenario for that would be to run your unit tests on the JVM, right, and record the configuration from whatever was happening. You can run your integration tests. You can run specific scenarios for just touch the code paths. You can do it, and you don't need to provide the configuration manually. So the reflection works, the proxies work, the other things work, and you can build non-trivial examples of the Java applications that are converted to native image. One of them is, very interestingly, the GraalVM compiler itself. So in the new versions of GraalVM, the GraalVM compiler, which is the Java application, right? I told you that it's written in Java, is compiled as a native image to a shared library, and it's put into the Java process as a shared library. So when you run GraalVM, so when I run those benchmarks, the compiler itself wasn't loaded as a jar file. It wasn't compiled during the runtime, but it was already built as a native library there. It was already native code. And how we got that code, we compiled the Java files into the native image. So you can get the idea, right? A compiler is a complicated piece of machinery, and it works. So it should work for other complex applications as well. And indeed it works, right? Indeed it works, and indeed it gives you great results for startup. There are a number of frameworks which say that they support GraalVM native images as the compilation target for their applications. And you can see that we measured some results, and normally it takes some time, not quite a bit of time. Milliseconds and seconds are actually maybe not the largest startup time ever, but it takes that much time to execute and start on the JVM, and when you compile it ahead of time with GraalVM, the startup becomes much smaller. There are differences in the exact implementations, but the main benefit for that comes from the GraalVM native image capabilities. The memory footprint as well, right? Because we don't include the machinery to do stuff with class files, the memory consumption becomes much smaller. Something like maybe five times smaller, or like 10 times smaller, depending on the exact application. But it is definitely, it can fit in the several dozens of megabytes rather than being in the hundreds. Spring applications, so this happened yesterday. Spring application and Spring team are looking forward to enable the support for GraalVM native images in Spring, and we are collaborating with the Pivotal engineers on this. So both them and us would like to see Spring applications work as a native images as well. There was some work done before. There were issues on GitHub raised and looked at and fixed. There were code changes on both sides, and we will continue doing that to support Spring applications as well. How many of you run Spring? Nice. So it's a pretty important project in the ecosystem, right? So we are looking forward to that. It will take a couple of months, but there are plans forward, and you can see the updated in real time page reflecting what is happening with that particular support in the Spring project, Spring framework GitHub. Right, so talking about peak performance of this, right? Because that's also important aspect. Yeah, we are good at startup, we are good at memory consumption, but are we actually good at running this code efficiently? Because just-in-time compilation has very good benefits for that. It can optimize, it can speculate, and it knows that if anything happens, if the code path changes or assumptions change, then you can just de-optimize and optimize again, right? Because you're at runtime, you have all that information. So when you compile ahead of time, you cannot just do that. There is no ability to de-optimize at runtime, because you will never be able to re-optimize again. So the code that you output with ahead of time compilation is final, right? It has to be more conservative. It cannot just assume that certain data will come in. How do you get the best performance with that? Well, the good bit is that you get predictable performance all the time, right? Because the code is set in stone. There is no dynamic optimizations happening. But it could be more conservative. So to get the best of the performance there, you want to use the profile-guided optimizations, which means that you would like to gather the profile for your runtime beforehand, again, and then use that profile information to suggest to the AUT compiler what code paths are actually important, which would be the hot paths or not. And you can see that we tested this on a sample web application. I think it was a Netty-based server that was respond with hello worlds or something, respond to the web requests. And we tested that, and you can see that on the JDK 8, the performance gets better with time, right? Because it starts slower and handles like a few thousand requests per second, but then it gets warmed up, and then it gets better than the GraalVM AUT native image option, which has a very predictable performance over the time. But if you get the profile-guided optimizations in, if you actually gather the profile and you run it and you get the optimized native image, you'll get a very comparable performance with the warmed-up jet. But you also get that from the very beginning of your service time. How does it work? You provide command line flags, you get the instrument binary, you get the relevant workloads run on it, and then you get the optimized binary as the output. Which in short means, yeah, you need to run your application beforehand, but you probably need to run it anyway, right? You probably have tests, you probably have staging environments, hopefully you have the environment where you do performance tests, and then you will get the optimized binary, which can perform on the level of a warmed-up jet, which is very not easy. Right, so that was the part about the native images. We have a great Polyglot support, and we can run applications in different languages. I've seen the session yesterday, and there was said that GraalVM cannot invoke Node.js from Java, for example. That is not true. We can invoke Node.js from Java. We cannot start Node.js from Java because Node.js wants to register some single handlers which are taken by the JVM, and they conflict, and it doesn't start that way. But we can start JVM from Node.js, and it works this way, and then you can do interop in both directions, which is interesting. Our JavaScript is compatible with the standards for the language, and it's fast, certainly faster than Nashorn. It's also available just as a bunch of jar files. So if you would like to run our JavaScript on your stock JDK, what you can do, you can enable it by just a bunch of Maven dependencies. You get the jar files, you configure them a certain way, and you use that. So if you are looking to run JavaScript on the JVM, certainly look into this direction. Our Ruby is fast. Our R is very fast. Our Python is getting more compatible with the ecosystem as we speak, right? The problem with those dynamic languages very often is that there are like native components there, right? There are native extensions that we will run code written in C or Fortran, and Python is no exception. If you are looking to do any machine learning, you will probably use some libraries that will probably use other libraries that will probably use NumPy or SciPy, which is the data representation for those things, which is written in Fortran. So when we run it all together, we would like to run both bits, the Python code, which runs, you can run snippets of Python easily on GraalVM, but we also would like to run the Fortran or the C code, and we would like to run them together. And there is the border, and when people write Python and C++, they very often are not considering that there could be different implementations of the runtime that would like to run both. So be mindful of the compatibility of Python. And there is a website, on the website there is a URL, a page where you can check how compatible are certain modules from the ecosystem. We download them, we run the tests, and we expect the tests to pass. If the tests pass, that means we as a platform do the expected things, which means that your application will run as well, right? So NPM module tests pass by like 99-point-something%, right? We know that we are compatible platform. Ruby and R tests pass, but a little bit less, and those languages are in the experimental shape right now. Python as well, so check that out, try it, but the key to happiness is having low expectations. Just try it again later as well. The tooling works for the languages altogether because they all work through the same tool chain, through the same framework. For running, you can use the same developer tooling for different languages. So you can debug your Ruby, R, and Python and JavaScript using the Chrome debugger, Chrome inspector, if you will. You can see what happens with the memory of those programs using a visual VM embedded with the GraalVM and being aware of the GraalVM Polyglot capabilities. There is a profiler included, so you can see what actually is happening. So the developer tooling is very common, and it works with the Polyglot applications as well. And I don't have time for demo, so find me later, and I will be happy. Actually, you can also check the blog posts. So, for example, this URL. We blog at medium.com/GraalVM, and we try to talk about interesting features so you can try it yourself. And also for the native code, there is a very interesting thing that I would like to show you, and I will do it. I have 50 seconds, so I will be very swift about this. What we can do, we can run LLVM bitcode in a managed mode. So when it tries to do random pointer access or right outside of the array boundaries, which normally would lead you to segfault or to security vulnerabilities, right? Terrible things. What we get back is, just let me let me just run this. So it's a gzip application that gzips files and unzips them, and I would like to decompress a file with a really long file name, and essentially it will throw at me an exception. And if I would like to use the compiled version of this, I will get the segmentation fault, right? And why I would do this, because the code is written this way, there is some C hacking was done by yours truly to implement a segfault, which wasn't trivial, by the way, to get a repeatable segfault there. So we're overwriting some memory within a short array, and you can see in the compiled world, the segmentation faults, nothing, and in the managed mode for LLVM boundary, we get the normal exception that says, oh, you are trying to write outside of the array, which is an excellent feature. Just very cool to show. Right, so GraalVM, high-performance polyglot virtual machine for running different things, embeddable as you would like, and there are a number of things that you would like to check GraalVM for, and I would strongly encourage you to do so, and I hope you would do so and come back to us with the feedback. Thank you very much.